Okay guys, so in this video we will discuss about the behavior of concrete, that how we can define the behavior in SAP 2000. For example, I'm not talking about defining the material, but I'm talking about defining its behavior, right? I hope you know the difference. So this is a predefined material of concrete in a SAP 2000, which has a name 4000 psi. You can go to modify show material and check the behavior, or you can add a copy of this material, or you can add new material. Let me take to modify show material properties, and all these things are predefined by the SAP 2000. You can just check that elastic modulus is 3604 or 5, which is nominal value for the concrete, normal weight concrete. Poisson's ratio is 0.2. All other properties are here. If you change the unit from kip inch to kip feet, you can see that the weight per unit volume is 0.15 kip per cubic feet, right? So uh, as soon as you click this switch to advanced property display, so here again the name is same, material type is concrete. Now what I want to show you is the directional symmetry type. So here you can pick up the required or well suited type, which one is suited for you. For example, there are four types of material defined in SAP 2000: isotropic, orthotropic, anisotropic, and uniaxial. So what are these different types? Let me show you. For example, here from this window, we see that the isotropic is a material where properties will not change with respect to direction, right? This is the definition of isotropic, that material properties will remain same in all the three directions. However, in orthotropic, the properties will change in mutually perpendicular direction, right? It can be changed in x and same in y and z, or it can be different in all three x, y, and z direction, all right? However, in anisotropic, it should be properties will change in all directions along the object, right? So it is changed in all directions. However, it will change in mutually perpendicular directions. So this is the difference between all the three materials. The metals and glass are classified as isotropic. For example, steel, aluminum, this is classified as isotropic. However, wood composites, they can be classified as orthotropic or anisotropic, right? So concrete, it is a composite. Masonry, it is a composite. So they can be classified as orthotropic material or anisotropic material. Now to define the isotropic material, you need two independent elastic constants. However, for orthotropic, you need 9, and for anisotropic, you need 21 independent elastic constants to define the material properly. All right. So let's go to the SAP interface. However, now let me show you that if I have selected isotropic here, so when I click the modify show material properties, see, I have to define elastic modulus, Poisson's ratio, and coefficient of thermal expansion in this section, and here the weight per unit volume and mass per unit volume along with the compressive strength. This is all data that I need to define isotropic material. Now keep in mind, and let me show you if I select orthotropic material, right? So when I click this button, just see the difference. The three values showing E1 in X direction, E2 in Y direction, E3 in Z direction. Previously it was like this. You can see the difference that E was constant in all three directions, U, A, everything was same in all the three directions. However, for orthotropic material, it is varying in all the three directions. Well, I mean, it may or may not. See, the values are here same here, but you can put different values in different directions for all these constants, right? And when you click the anisotropic material, so just see 3, 6, 12, and 15. There are 27 independent properties that need to be defined, right? So this is the main difference between the three types in SAP 2000. Or there is another type which is called uniaxial, and I hope you all know that. What does uniaxial means? It takes material to be as a acting in one direction, uniaxial direction. There is no second direction, just like a beam element. And if you click it, see, there is no Poisson's ratio. Why there is no Poisson's ratio? Because it is not considering the lateral strain, or there is no shear modulus because it is considering only longitudinal direction. So these are the four different types of materials in the SAP2000 that you can select for your desired purpose, and then you can see that which one fits your requirements. Okay, so if I click the isotropic and I click this one, we have discussed this interface. Now there is a button here which is called non-linear material data. So if you click it, another window will appear, right? In this window, you can make sure the material name and material type, and you can come to the next step where the hysteresis type is given. What is hysteresis type? SAP has given two different types of hysteresis curves, three different types, sorry, elastic, kinematic, and Takeda. So let me take you to these three different types of curves. Uh, this is the Takeda model. See, the Q hysteresis force displacement model of a reinforced concrete column, Takeda in 1979. So if you start from this point, 0, 0, the K1 is your stiffness till yield point. Then from yield to ultimate, your stiffness is K2, and this is your unloading direction. So this is your permanent deformation. And similarly, in negative loading in negative direction and reloading. So this is the Takeda model, which was defined in 1979, and you can use this model for your concrete element, or you can just use simple elastic model. See, it is starting from 0, 0, the loading direction, and the unloading direction is ending at the 0, 0. So there is no permanent deformation whatsoever. And this is the kinematic model, your K1, K2, then unloading, this is your K3, then reloading in negative direction, and then it is going so on. So these are your three different material models that you can define for your hysteresis curves in SAP 2000.